video is on colligative properties. In the course of this video, I hope you learn how to do a few things, including being able to describe colligative properties and how they function. And you should be able to qualitatively describe the effect that colligative properties will have in boiling point, elevation, freezing point, depression, vapor pressure, and osmotic pressure. And importantly, you should be able to calculate the change in vapor pressure and osmotic pressure due to solutes that are present in the solution. Okay, colligative properties. So properties that change due to the presence of solutes. And the great thing about colligative properties, it doesn't matter what those solutes are. It only matters the number and molarity of those solutes. So we're going to take a look at four different colligative properties. The first one is vapor pressure. Okay, we may remind ourselves that vapor pressure is the ability of molecules to escape from the liquid phase into the gas phase. And this is before the boiling point. So at any temperature, there are some number of molecules that just randomly are able to get enough energy to break free from the molecular interactions and fly off into the vapor phase. So if we stop this simulation in midstream, we can see that there are one, maybe two molecules that are sitting in the vapor phase that have broken free of that. Right, so this has to do with the molecules that are colliding at the surface of the solution. And the idea behind colligative properties is that these things just get in the way. So the solutes or the salts or molecules that we stick into the solution, which generally are non-volatile, that these things just get in the way and prevent things from running into each other and escaping from the surface. And so we can picture this simplistically as just putting some blocks that get in the way. So I will not have as many in the simulation. I will not have as many molecules escaping into the vapor phase, because there's just not as much surface area available. And the surface area is being taken up in colligative properties. The surface area is being taken up by the solutes, the things that we've dissolved into our solution. And this is the model that we want to have for colligative properties, that stuff just gets in the way and prevents things from happening. In this case, my vapor pressure that I observe when I have a bunch of stuff dissolved in a solution is going to be less than the vapor pressure that I would observe without anything there. And it's just things at the surface in this case are preventing molecules from escaping and going into vapor phase. For vapor pressure in particular, we have a way of quantitating this. We call this Raoult's law, which says that the vapor pressure that we observe is equal to the mole fraction of the solvent times the vapor pressure that we would expect to observe for that solvent under standard conditions. Notice the mole fraction here. It's important how we calculate the mole fraction. Mole fraction is going to come from the number of moles of particles. So if we have water, it's going to be one molecule is going to provide one particle. If I have something like sodium chloride that's dissolved, notice that I have ions that will separate, and I'll have two ions that represent one mole. And so this is going to be the mole fraction, the ratio of the number of moles of particles that are present. And one way to look at this is to look at the surface. So if we look at the top down, the surface of a liquid, and what we'll see that we have a number of, in this case, water molecules floating around, and we have these ions floating around and taking up space. And the key part here is that colligative properties depends on the number of particles that are there. In this case, I can pretend this is sodium chloride, so I have my positive ions, my negative ions. These are floating around, and these are getting in the way and preventing things from happening. All right. So Raoult's law is a way of calculating the effect on vapor pressure. So my vapor pressure is going to be less than the pressure that it would be when I have just a pure solution. And the salts just get in the way of preventing things from escaping. Freezing and boiling points are going to be similar effects. So if I take my simulation and I lower the temperature down, I'll see my molecules start moving more slowly, and they start trying to come together to form some sort of crystal structure that we'll know as ice. But notice what's happened to these positive and negative charges. So in this case, my salt, I can call it sodium chloride, is getting in the way, preventing formation of this nice crystal lattice structure that forms a solid. And in this case, to form a solid, this means I have to slow things down a little bit more, or in other words, I have to lower the temperature a little bit more. So there will be a freezing point depression because those salt molecules are getting in the way. Same thing happens if I increase the temperature, that as I increase the temperature, I need things to escape into the vapor phase. And just like vapor pressure, that I have things on the surface that are in the way, so I'll have fewer things escaping into vapor pressure. And so I'll have an elevation of my boiling point because I have things that are getting in the way. Notice this is not like intermolecular forces, where if we have stronger intermolecular forces, I have something that will both boil and freeze at slightly higher temperatures. Here I have increased my boiling temperature and I've decreased my freezing temperature. So the range that it stays in a liquid phase is greater. So if I have salt water, it's going to be in a liquid phase for a longer period of time over a wider temperature range than pure water by itself. So my freezing point gets depressed. It's hard to structure that into a crystal structure, and my boiling point gets elevated. It's harder for those things to escape into the vapor phase. Okay, the last thing we want to talk about is osmosis. So this is a colligative property in the sense that it doesn't matter what the solute is, that the number of molecules is what matters. Osmotic pressure. So if you take a tube that's shown here in the initial state, and I have a different number of solutes dissolved in the water that's on the left versus on the right. And I put in there a semi-permeable membrane, which means my solvent can go through, but my solute particles or my dissolved salt cannot. And so what happens is my solvent moves to the side to equilibrate. And it'll move to the side that has a higher concentration until I end up with roughly a similar concentration of solute that's dissolved. And it will do this independent of what the salt is. When this is done in a tube that's shaped like this, I'll have a difference in height or a difference in pressure that comes from having higher pressure now possible on one side of my membrane than on the other side. And this was established by having a different concentration of salts on either side of my osmotic tube. This difference in pressure, we're going to call this osmotic pressure. So this is the pressure that we're interested in finding and calculating. So the pressure that we're going to measure is going to be the pressure that's required to stop osmosis. And this is going to be called osmotic pressure. You may recall the ideal gas law, where we have pressure times volume equals number of moles times my gas constant times temperature in Kelvin. Osmotic pressure is very similar to that. So this is going to be the same idea that we have some pressure, osmotic pressure. We're going to give it this pi symbol. And this times volume equals nRT. We can move volume, and we have number of moles divided by volume, or the molarity. So my osmotic pressure, pi, is going to be equal to the molarity times my gas constant times the change in temperature. This provides me a nice way to measure that difference. This is a very common thing, so you may have heard of reverse osmosis. So the idea that we can purify water, in this case, anybody been to Culligan, they have a reverse osmosis system that they use there. There we have a way of reversing pressure, so we'll force the water through that membrane. The membrane will not allow the solutes to get through, and by forcing the water through there, we end up having purified water. Okay, well, can you now explain how colligative properties work? Can you calculate boiling point elevation, freezing point depression? Can you explain osmotic pressure? And can you calculate osmotic pressure as well? I hope you can. Thank you.